The jet stream explained how it controls our weather. Imagine standing in an open field on a windy day, feeling the air rush past you. Now imagine traveling 30,000 feet straight up, where commercial jets cruise. There, invisible rivers of air race across the planet at speeds that would put a Formula One car to shame, sometimes exceeding 200 miles per hour. These are the jet streams, and they're the puppet masters of our weather. Today, we're going on a journey into the sky to understand one of Earth's most powerful and least visible forces. This isn't just about why your flight might be faster going east than west. It's about the atmospheric rivers that determine whether your city gets drought or deluge, heat wave or cold snap, calm or catastrophe. By the end of our time together, you'll understand what jet streams are, why they exist, how they shape the weather you experience every single day, and why they're changing in ways that matter for everyone on Earth. So settle in, look up, and let's explore the rivers in the sky. Part 1, The Discovery. Wartime Revelation, the story of the jet. Stream begins with a terrifying moment during World War II. On November 24th, 1944, American B-29 bombers were flying a mission over Tokyo at 30,000 feet. The pilots expected to cruise at about 230 miles per hour. Instead, ground speed readings showed they were barely moving, sometimes going backward despite full throttle. The crews had encountered winds so powerful they could pin giant bombers in place. Japanese meteorologists had known about these high-altitude winds for years, but this was the first time Americans experienced them directly. They discovered the jet stream, though they didn't fully understand what they'd found. After the war, meteorologists began to piece together the puzzle. What seemed like a local phenomenon over Japan was actually part of a global system of high-altitude wind rivers circling the planet. These weren't just strong winds, they were organized, predictable, and absolutely fundamental to how Earth's atmosphere worked. Think about that for a moment. Humans had been observing weather for thousands of years, but we only discovered one of its primary drivers in the 1940s. It's like studying the ocean for millennia without knowing about currents. What exactly is a jet stream? At its simplest, a jet stream is a narrow band of very strong winds in the upper atmosphere, typically between 5 and 9 miles above Earth's surface. But calling it just a strong wind is like calling the Amazon just a big river. Jet streams are organized, persistent atmospheric features that snake around the planet, like rivers through the sky. Picture a ribbon of air, maybe a couple hundred miles wide and a mile or two thick, flowing around Earth. Wind speeds in the core can reach 250 miles per hour or more, though they're typically between 100 and 150. The edges of the jet stream have slower winds, creating a gradient from the racing core to the calmer air around it. There are 4 major jet streams on Earth, 2 polar jets and 2 subtropical jets. The polar jet streams, found in both hemispheres between 30 and 60 degrees latitude, are the ones most people mean when they talk about the jet stream. They're stronger, more variable, and have the biggest impact on day-to-day weather in places like North America and Europe. The subtropical jets sit closer to 30 degrees latitude in each hemisphere. They're typically higher, weaker, and more consistent than the polar jets. They influence weather too, particularly in regions closer to the tropics. But the polar jets are the weather makers that affect most of the world's population. Why do they exist? To understand why jet streams form, we need to think about temperature differences. The fundamental engine driving jet streams is the temperature contrast between the equator and the poles. The equator receives direct sunlight year-round. The poles, tilted away from the sun for half the year, receive far less solar energy. This creates a massive temperature gradient from hot tropics to cold poles. Nature abhors such imbalances and constantly works to even them out. Heat moves from warm to cold. That's basic thermodynamics. But on a rotating planet with an atmosphere, this heat transfer doesn't happen through simple north-south winds. Instead, it creates complex circulation patterns, and at the boundary between different air masses, where cold polar air meets warmer air from lower latitudes, the jet stream forms. Here's where physics gets interesting. Warm air is less dense than cold air, so it occupies more vertical space. Imagine 2 columns of air, one warm and one cold, both pressing down on the surface with the same pressure. The warm column has to be taller to contain the same amount of air, This height difference creates a pressure gradient in the upper atmosphere, and air flows from high to low pressure. But we're on a spinning planet. Earth's rotation adds a twist literally. The Coriolis effect, caused by Earth's rotation, deflects moving air to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection, combined with the pressure gradient, doesn't create a simple north-south wind. Instead, it creates a west-to-east flow, the jet stream. Think of it like water swirling down a drain, but stretched around an entire hemisphere. The result is a fast-moving river of air that flows generally from west to east, separating cold polar air to the north from warmer air to the south. Part 2. Anatomy of the jet stream, the meandering. Path. If you could see the jet stream from space, you wouldn't see a straight band circling the planet. Instead, you'd see a snake-like pattern of waves and curves, called Rossby waves after the Swedish meteorologist who explained them. The jet stream constantly meanders north and south as it flows around Earth. Sometimes these meanders are gentle, with the jet stream following a relatively straight path. Other times, the waves become large and amplified, with the jet stream plunging far south in some places and bulging far north in others. These meanders aren't random. They're created by the interaction between the jet stream and features on Earth's surface, mountain ranges, land-ocean contrasts, and temperature differences. The Rocky Mountains, for instance, can force the jet stream into a particular wave pattern that influences weather thousands of miles downstream. When you see a weather map showing ridges and troughs, you're looking at these waves. A ridge is where the jet stream bulges poleward, typically bringing warm conditions. A trough is where it dips equatorward, usually bringing cooler weather. The position and strength of these features determine much of the weather experienced below. Fast and slow lanes within the jet stream itself. Wind speeds vary dramatically. The fastest core, called the jet streak or jet max, is where winds reach their peak. These regions of maximum wind are particularly important. For weather development, air entering a jet streak accelerates, and air leaving it decelerates. This acceleration and deceleration create areas of rising and sinking air below the jet stream. Rising air is where storms develop sinking. Air suppresses storm formation. Meteorologists pay close attention to the left exit region of jet streaks. That's the area just downstream of the fastest winds. On the left side, if you're looking in the direction the wind is blowing, this is a prime location for storm development because it's where rising air is strongest. Commercial pilots love jet streams. When flying west to east, they can shave hours off transcontinental flights by hitching a ride on these high-altitude winds. Flying against the jet stream going east to west adds time and burns more fuel. Your flight time from New York to Los Angeles is typically longer than the return trip. And the jet stream is why. Seasonal shifts. Jet streams aren't static. They shift position and intensity with the seasons, and these shifts have profound impacts on weather patterns. During winter, the temperature contrast between pole and equator is strongest. The pole receives no sunlight for part of the winter, creating extremely cold temperatures, while the tropics remain warm. This strong temperature gradient powers a stronger, faster jet stream that typically sits farther south. A strong winter jet stream brings frequent storms, especially to mid-latitude regions. Storm systems ride along the jet stream like boats on a river, following its path. When the jet stream dips south over a region, it opens the door for cold air outbreaks. When it lifts north, warmth floods in. Summer weakens the temperature gradient. The pole receives constant daylight, warming significantly, while tropical temperatures don't change much. The result is a weaker jet stream that retreats farther north. This is why summers in the mid-latitudes are generally calmer, with fewer powerful storm systems. But these aren't just gradual, predictable seasonal changes. The jet stream can experience rapid shifts in position and intensity, sometimes in a matter of days. A sudden shift can transform weather across an entire continent almost overnight. Part 3. The weather maker steering the storms. Every storm system you've ever experienced, every hurricane approach, every blizzard, every atmospheric river moved where it did because of the jet stream. It's the conveyor belt of the atmosphere, steering weather systems along its path. Low-pressure systems. The spinning areas of rising air that bring precipitation form preferentially in certain locations relative to the jet stream. They then travel along and beneath it, guided like trains on tracks. Where the jet stream goes, storms follow. When the jet stream takes a winding, meandering path, it can create what meteorologists call blocking patterns. Imagine the jet stream forming a large loop, like an omega symbol. Air trapped inside these loops can sit in place for days or even weeks, leading to persistent weather patterns, extended heat waves, prolonged droughts, or multi-day rain events. The Pacific Northwest floods of recent winters, a jet stream stuck in a pattern that continuously funneled moisture-rich Pacific air directly into the coast. The European heatwave of 2003 that killed tens of thousands. A blocking pattern parked a ridge of high pressure over the continent for weeks. The polar vortex outbreaks that bring Arctic air deep into the United States. The jet stream diving unusually far south, opening a pathway for that cold air. Understanding where the jet stream will be next week is one of the most critical aspects of weather forecasting. Get that right. And you can predict broad weather patterns with reasonable confidence. Get it wrong, and your forecast will be off by hundreds of miles and many degrees, temperature boundaries. The jet stream marks a boundary in the sky, and that boundary matters down here at the surface. On one side sits cold air, on the other, warm air. The position of this boundary determines whether you're wearing shorts or a winter coat. When the jet stream sits to your north, you're typically in the warm sector, experiencing air that originated from lower latitudes. When it's to your south, you're in the cold sector, feeling air that came from higher latitudes. And when the boundary passes directly over you, that's when things get interesting. The frontal systems you see on weather maps, cold fronts, and warm fronts air surface expressions of these temperature contrasts. Aloft, the jet stream marks where these different air masses meet. The stronger the jet stream, the sharper the temperature contrast, and the more energetic the weather systems that form. Think about a typical winter storm in the eastern United States. Cold air floods south from Canada. Warm, moist air surges north from the Gulf of Mexico. The jet stream marks where these air masses collide. And from that collision, a powerful storm system develops. Rain to the south, snow to the north, and ice in the transition zone, where the battle between air masses is most intense. The rainmaker and rain blocker precipitation patterns across the globe owe much to the jet stream's position and behavior. When the jet stream flows over a region, it promotes rising air, clouds, and precipitation. When it stays away, high pressure and dry conditions dominate. The American West Coast provides a perfect example. During winter, when the jet stream sits farther south, it frequently directs Pacific storms directly into California, Oregon, and Washington. This is when these regions receive most of their annual precipitation. During summer, the jet stream lifts north into Canada, and the West Coast dries out, entering its characteristic Mediterranean dry season. But year-to-year variations matter enormously. A jet stream that sets up in just the right position can funnel storm after storm into California, bringing flooding rains and mountain snow. This is what breaks droughts. But if the jet stream shifts just a few hundred miles north, those same storms bypass California entirely, and drought continues or intensifies. Atmospheric rivers, those narrow corridors of intense moisture transport responsible for the biggest precipitation events on the west. Coast air intimately connected to the jet stream. They form in specific locations relative to low-pressure systems, and the jet stream steers both the storms and the moisture plumes they produce. Across the Atlantic, Europe's weather is similarly controlled. When the jet stream flows strongly from west to east across the Atlantic, it brings frequent storms and mild, wet conditions to Western Europe. When it weakens or shifts, weather patterns change dramatically. A southern track brings Mediterranean storms. A northern track leaves Europe dry but brings storms to Scandinavia. Extreme events, the jet stream's most dramatic. Influence comes during extreme weather events. When it behaves in unusual ways, extreme weather follows. Record heat waves almost always involve the jet stream bulging far poleward, creating what meteorologists call an omega block or heat dome. Under these ridges, air sinks, compresses, and heats up. Sinking air prevents clouds from forming, so sunshine beats down relentlessly. The same air keeps recirculating, getting progressively hotter. Meanwhile, the jet stream locked in this configuration prevents cooler air, or storm systems from breaking the pattern. Record cold outbreaks involve the opposite, the jet stream diving unusually far equatorward. allowing polar or Arctic air to flood into regions that rarely experience it. When this happens, temperature records don't just break, they shatter. Places like Texas or Florida can experience temperatures more. Typical of Canada or the northern plains, flooding events often occur when the jet stream gets stuck in a configuration that repeatedly directs moisture-laden storms into the same region. Imagine a fire hose pointed at your house, but the hose is made of atmospheric rivers, and it stays pointed at you for days or weeks. That's what a stuck jet stream pattern can do. The ingredients for extreme weather have always existed in the atmosphere, but the jet stream is the mixer, the organizer, the pattern maker that takes those ingredients and creates events that make headlines and rewrite record books. Part 4, A Changing River, the Arctic Amplification Connection. Here's where our story takes a concerning turn. Remember that the jet stream exists because of the temperature difference between the equator and the poles. That difference is changing, and not in a small way. The Arctic is warming faster than any other region on Earth, about 4 times faster than the global average. This phenomenon, called Arctic amplification, is melting sea ice, thawing permafrost, and dramatically reducing the temperature contrast between the Arctic and mid-latitudes. Think about what this means for the jet stream. Its power comes from that temperature gradient. Weaken the gradient, and you affect the jet stream's behavior. It's like reducing the slope of a river. The flow becomes slower and more meandering. Scientists have observed that the jet stream is indeed becoming wavier, with larger north-south meanders. This matters because those big meanders are what create persistent weather patterns, the kind that lead to extreme events. A wavy jet stream means weather patterns can get stuck for longer periods, turning hot spells into heat waves, dry periods into droughts, and rainy stretches into floods. The mechanisms are complex and still being researched, but the basic principle is straightforward: change the temperature distribution. And you change the jet stream, and you change everything about weather patterns. Stuck patterns and extremes evidence is mounting. That blocking patterns, those stuck jet stream configurations, are becoming more common and more persistent. This has enormous implications for extreme weather. Consider recent events. The 2010 Russian heat wave and Pakistan floods were linked to a single massive blocking pattern. The 2013-2014 California drought coincided with a persistent ridge off the west coast that meteorologists dubbed the ridiculously resilient ridge. The 2021 Pacific Northwest heat wave that killed hundreds involved a record-breaking heat dome that stubbornly refused to move. When weather patterns stick, moderate conditions become extreme. A warm week becomes a heat wave as temperatures keep climbing. A dry period becomes a drought as the absence of rain stretches on. A storm track that brings welcome rain can become disastrous flooding. When the pattern won't budge, the jet stream has always been variable. That's its nature. But scientists are concerned that we're seeing changes in how that variability expresses itself, with implications for the frequency and severity of extreme weather events. Polar vortex disruptions. You've probably heard the term polar vortex in news reports about extreme cold outbreaks. The polar vortex is a large area of low pressure and cold air that sits over the poles, particularly strong during winter. The polar jet stream encircles it, acting like a fence that keeps the cold air penned. Up in the Arctic, when this fence is strong and tight, cold air stays in the Arctic where it belongs. But sometimes, the polar vortex becomes distorted or splits, and the jet stream weakens and meanders wildly. This allows Arctic air to spill out, plunging far south and bringing extreme cold to places unaccustomed to it. Research suggests these polar vortex disruptions may be becoming more common as the Arctic warms. The mechanism is still debated, but the idea is that rapid Arctic warming and reduced sea ice alter atmospheric circulation patterns in ways that make the polar vortex less stable. The result is paradoxical. A warming Arctic contributing to extreme cold outbreaks in mid-latitudes. It's not that the world is getting colder, it's that the warming Arctic is changing atmospheric circulation in ways that occasionally allow cold air to flood southward. Even as average global temperatures rise, what the future holds, predicting exactly how the jet stream will change in a warming world, remains one of the most challenging questions in climate science. Models agree that the Arctic will continue warming faster than lower latitudes, which will continue to weaken the temperature gradient. But how this translates to specific jet stream behavior is complex. Some aspects seem likely. Seasonal shifts in jet stream position will probably change, potentially altering precipitation patterns. The intensity and duration of blocking patterns may increase. The jet stream's average position might shift poleward, changing which regions experience its influence, but other aspects remain uncertain. Will the jet stream become uniformly wavier, or will changes vary by region and season? How will shifts in tropical weather patterns interact with mid-latitude jet stream changes? Will certain types of extreme events become more common while others become less so? What's clear is that changes to the jet stream will affect everyone. This isn't some distant, abstract climate impact. The jet stream determines whether your region gets rain or stays dry, whether you face heat waves or cold snaps, whether storms hit your area or bypass it entirely. Changes to this fundamental feature of our atmosphere will reshape weather patterns globally. Part 5, Living with the Jet Stream Better. Forecasting understanding the jet stream has revolutionized weather forecasting. Modern forecasts can predict weather patterns reasonably well, up to 7 to 10 days in advance, and much of that skill comes from modeling the jet stream's behavior. Supercomputers run sophisticated models that simulate atmospheric physics, calculating how the jet stream will evolve. Meteorologists analyze these projections, looking at where the jet stream will be positioned, how strong it will be, and what patterns its meanders will create. When forecasters talk about uncertainty in a prediction, it's often uncertainty about jet stream behavior. A shift in the jet stream's position by just 100 miles can mean the difference between a major snowstorm and a non-event, between flooding rains and light showers, between record heat and pleasant conditions. Recent advances in satellite technology and data assimilation are improving our ability to observe and predict the jet stream. Every additional day of reliable forecast skill has enormous economic value, allowing better preparation for extreme events, more efficient agriculture, improved energy management, and countless other benefits. But there are limits. The atmosphere is chaotic, and small uncertainties grow over time. We'll probably never be able to predict specific weather conditions weeks or months in advance, but understanding jet stream patterns and how they're likely to evolve in a changing climate helps us anticipate broader trends. Adapting to change as jet stream behavior changes. Adaptation becomes crucial. Regions dependent on jet stream-driven precipitation patterns may need to rethink water management. Agricultural zones may shift as weather patterns change. Infrastructure designed for historical weather extremes may need upgrading for new realities. This isn't about panic or despair. It's about intelligent preparation for a changing world. We've adapted to changing conditions throughout human history. The difference now is that we can see changes coming and plan accordingly. Water systems in the American West, for instance, were built around historical precipitation patterns. If the jet stream's typical winter position shifts, bringing storms to different locations, those systems may need reimagining. This is already driving innovation in water storage. Efficiency and allocation. Energy grids face similar challenges. Wind patterns are changing, affecting wind power generation. Temperature extremes stress grids during peak demand periods. Understanding how jet stream changes affect these patterns helps in planning more resilient energy systems. The bigger picture. The jet stream story is ultimately a climate story. It's one of the most visible ways that Arctic warming and changing global temperature patterns affect daily life. You might not feel the Arctic warming directly, but you feel it when the jet stream behaves differently, creating weather patterns that weren't common before. This connection from rising greenhouse gas emissions to Arctic, amplification to jet stream changes to altered weather patterns shows how interconnected Earth systems are. Change one part, and effects ripple through the whole system. But understanding these connections empowers us. We know what's driving changes. We know that stabilizing the climate means stabilizing these atmospheric patterns that govern our weather. We know that every action to reduce emissions helps preserve the climate patterns that human civilization developed within, appreciating the invisible. Next time you check the weather forecast, remember that invisible river in the sky. When you see a storm approaching, know that it's following a path carved by the jet stream. When you experience unusually warm or cold conditions, understand that the jet stream's position is playing a role. There's something profound about realizing that winds 5 miles above your head are determining whether you need an umbrella today, that this vast atmospheric river, powerful enough to blow bombers backward and stretch around the entire planet, is constantly shifting, constantly influencing, constantly shaping the weather we experience. The jet stream is a reminder that we live at the bottom of an ocean of air, one that's in constant motion, driven by heat from the sun and the spin of the planet. It's been shaping weather patterns for as long as Earth has had an atmosphere with these characteristics. It will continue long after we're gone. Conclusion. Rivers in the sky, we've traveled from a wartime discovery to the cutting edge of climate science, from basic physics to extreme weather events, from past behavior to future changes. The jet stream, once unknown, is now understood as one of Earth's fundamental atmospheric features. These rivers in the sky, racing around the planet at hundreds of miles per hour, are the puppet masters of weather. They steer storms, mark temperature boundaries, create precipitation patterns, and occasionally generate the extreme events that make headlines. Understanding them is understanding weather itself. The jet stream story is also a reminder of how much we've learned about our planet and how much remains to discover. A phenomenon that humans didn't know existed 80 years ago is now central to how we understand and predict weather. Every day, meteorologists track its movements, predicting where it will flow and what weather patterns it will create. But it's also a story about change. The jet stream that shaped weather patterns throughout human history is responding to a warming world. The temperature gradients that power it are shifting. Its behavior is evolving, and because it's so fundamental to weather, these changes matter for everyone. The good news is that we're not blind to these changes. We can observe them, study them, and prepare for them. We can work to stabilize the climate and preserve the atmospheric patterns that human civilization depends on. We can adapt where necessary, building resilience into our systems and societies. The jet stream will continue its endless race around the planet, marking boundaries, steering storms, shaping weather. It's been doing this for millions of years. What changes now is our relationship with it, to our understanding of it, our ability to predict it, and our recognition that our actions affect it. Look up, 5 miles straight up. The jet stream is flowing right now, an invisible river rushing through the sky. It's determining the weather you'll experience tomorrow, next week, and for seasons to come. It connects the Arctic to the tropics, the Pacific to the Atlantic, one side of the planet to the other. We live under rivers in the sky. Understanding them helps us understand our weather, our climate, and our changing world. That understanding is power to predict, to prepare, to adapt, and ultimately, to make better choices about our planet's future. The jet stream story is far from over. It's a continuing tale written in wind and weather, recorded in data and observations, interpreted by scientists and forecasters, and experienced by every person on Earth. It's a story of invisible forces shaping visible consequences, of global patterns determining local weather, of physics in motion above our heads every single day. And now it's a story you understand. The next time the weather changes dramatically, the next time you hear about extreme heat or cold, the next time storms march across your region, you'll know something most people don't, somewhere above it all. The jet stream is flowing, doing what it's done for millions of years, but in a world that's changing in ways we're only beginning to understand. That's the jet stream weather's hidden hand. The river in the sky, the invisible force shaping the air around us. It's always there, always flowing, always mattering. And now you know its story.